Okay, 5.5. So 5.5 is Dalton's law of partial pressures. Here's what it alludes to. Dalton's law of partial pressure talks about mixtures of gases and how a mixture of gases can affect the pressure of a sample. Thus far, as we've been doing these problems in section 5.3 and 5.4, we've typically only been talking about one gas and its effect on the pressure of a container. But it's rare that you just have one isolated gas. I mean, even the gases that are hitting us right now, that's not just one isolated gas, that's a bunch. Nitrogen, oxygen, carbon dioxide, water vapor. And if we have a combination of gases, that affects the total pressure in the room. So this is Dalton's law. It's pretty simple in that it just says the total pressure in a container equals the sum of the individual pressures of each of the gases. So if we wanted to know the total pressure in the room right now, all we'd have to do is look at a barometer. And the barometer would tell us the pressure in the room. I'm assuming it's something like 0.98, something like that. Okay. If we wanted to know the pressure of only the nitrogen, we'd have to use Dalton's law of partial pressure. Because even though nitrogen makes up the bulk of the gases that are inside of the room, it isn't the only thing that's contributing to that 0.98 atmospheres. Oxygen, carbon dioxide, water vapor, all of those other gases are also contributing. Okay. So this is just Dalton's partial pressure in words. No, it isn't. Because when you're figuring out average atomic, it's the last portion of that. It's the last step of that, yes. Where you add up each of the individual atomic masses, yeah. There's no weight percentage here yet. There will be a weight percentage in a little bit, but not yet. So we're going to do an example of this today, just a short little activity, collecting some water and trying to guesstimate how much carbon dioxide I can accumulate. And I have a little handout that shows you the technique we're going to use to do that. You'll see this picture on one of your handouts. Okay. Whenever you're producing a gas and you want to collect that gas, there's a couple of ways that you can go about it. But this is probably one of the easiest and one of the cheapest methods. It's collecting gas via what we call water displacement. All we do is take a full bottle of water, and we take that bottle. This is my bottle of water. And I'll take that bottle and I'm just going to invert it into a trough, okay, or an aquarium like I have today. And obviously, if you do it quick enough, that bottle is going to stay full even though it's tipped over, okay, because there's no reason for the water to leave even though it's tipped over because there's water in the trough. If you connect a hose to the bottom of the bottle, okay, like we have done here, and you produce some gas on the other side of the hose, like this reaction is actually doing. Okay, there's the reaction that's taking place. You're going to force the gas that's produced, in this case oxygen, to run up the hose. And that oxygen is going to start to fill that bottle. Okay? So at the end of the day, how could you tell me how much gas you collected? Well, you could, but I don't want theoretical yield. I want actual yield. From the experiment, how could you tell me how much gas you produced? How much water was displaced? Yes. Yeah. So initially, what you'd have to know is, well, how much water is right here. Okay. You run your reaction. You're going to have a bottle that hopefully still has a little bit of water inside of it. Okay, right here. And then you'd have to just do a little bit of subtraction, right? And that subtraction is going to give you the amount of gas that's in that space. Make sense? Okay. So that's just finding the volume of a gas via water displacement. Oxygen's not explosive. Oxygen is flammable. There's a little bit of a difference there. Because it's not really pressurized, it's not going to explode at all. But if you put a burning splint inside of it, it'll glow brighter. It'll glow a lot brighter because it is pure oxygen. The reason like a tank of oxygen is explosive because it is so pressurized. So if you were to light the tank on fire, it's flammable. It burns. Oxygen, helps burning. But then the molecules start moving a lot faster, obviously, because now they're hot, and they don't like being contained inside the walls of the gas tank, so they explode the tank, right? It would be dangerous, and I wouldn't want to be around it, but if you give me the option of being around a burning oxygen tank and a burning hydrogen tank, I will take the former instead of the latter. A hydrogen tank, there'd be issues. Yeah, people would lose jobs and limbs and probably lives. Not in that order, particularly. Okay. So if we're running this experiment, if we're running this particular experiment and we're interested in the amount of pressure that's in the top of this bottle, we have to take into account the fact that the top of the bottle is not completely oxygen gas. Water constantly evaporates. Constantly. Now, obviously, it evaporates quicker at hotter temperatures. But even at cold temperatures, water is evaporating into the gas phase. So if you allow a sample of water to sit for a while, water molecules in the liquid state are going to venture off into the gas state. So in my area right here, I have not only oxygen, but I also have water molecules adding to my total pressure. So I have to use Dalton's law of partial pressures to figure out the total pressure inside the top of that bottle. Okay? All right. The other side of the sheet that I gave you there is kind of a visual of how this occurs. And it's going to show you that just by mixing a couple of gases, we know that that's going to alter the pressure a little bit, but it should also show you something about the amount of the gases that you mix. Okay? So here we've got pressure 1, that's your red gas, and here we've got pressure 2. And Dalton's law of partial pressure says that if volume and temperature are constant, we want to hold those two constant, by the way. And we show that in this image by showing that disc, that silver disc at the same height. If volume and temperature are constant, then the pressure is going to be an addition of those two. What's interesting is to ask this question. What if I put more greens in there? What if I put more greens in there? What's going to happen to that? It's going to increase it. So, pressure is reliant upon what? The total number of molecules. So we're going to have to figure that out. We're going to have to take into account the total number of particles that are in the room. In this room right now, like I keep saying, you've got nitrogen, oxygen, carbon dioxide, and water vapor contributing to the total pressure. The total pressure is about 0.98 atmospheres. But do they all contribute equally? They don't. Which one contributes the most? Yeah, nitrogen. It's the most abundant gas inside of the room. Okay, so it's all about abundance. Oxygen contributes the second most, and then, I don't know, water or carbon dioxide, one of the two. Hi, Mrs. Hummel.
Hi, could I see Sarah and Edith real fast, please?
Sure, no problem. Yep. All right. So we have to take that into account. We have to figure out how to adjust for that fact. Now, this slide's going to get pretty mathematical. And I guarantee you by the end of the slide you're going to go, what? Huh? It'll help when we do an example problem. So just bear with me for the next slide. All right, consider a case in which two gases, A and B, and notice A is in red and B is in green. That's kind of going to help me follow the flow all the way down. Let's say that we were just concerned with the pressure of gas A. Could we find that? Well, sure. As long as we knew the number of moles of gas A, we could easily find the temperature. And volume shouldn't be a difficult thing to find either. If we were doing water displacement, we just have to find the amount of water actually displaced. And that would contribute to the amount of volume. Is the volume the same or different for the greens and the reds? It's the same. It's tricky. That's tricky. Because you always think, if I've got two different substances, well, they take up different amounts of volume. No, not for gases. And remember why that is. It's the incredible distances between the gas molecules that allows two gases to mix, but still keep the same volume. Could you ever mix two liquids together and keep the same volume? No, okay? So specific for gases. Another reason why gases are so different. All right, Na is the number of moles of A. Let's look at that same consideration for my other gas, gas B. Okay? Now again, I don't think it's a stretch to understand that if we wanted to know the pressures of each individual gases, and we were lucky enough to know the number of moles of each individual gases, we could certainly find that pressure without a lot of difficulty. Now what can we say about R, T, and V in both of those equations? They're constant, they're equal, they're the same. Yeah. So we can do a little bit of algebra. We can say, well, the total pressure, well, this isn't the algebra. This is Dalton. And Dalton says the total pressure of our cylinder on the right side is equal to the pressure of A plus the pressure of B. And I said before that our pressure is going to be dependent upon the amount of molecules for a specific gas. Again, nitrogen gives more pressure to the room than the oxygen does. So we have to account for the total number of moles. And that's what this factor is going to help with, this XA. X is standing for the ratio, the mole ratio. In this room, the mole ratio for nitrogen is about 0.76. So that just means there's about 76% nitrogen. Okay? For my example up on the board, the mole ratio is for the gas A, is just the number of moles of A divided by the total number of moles. I've only got two gases, so the total number of moles is just the moles of A plus the moles of B. We can do the same thing for gas B. We just have to kind of put moles B on top instead of moles of A. So, we can make the following statement. The total pressure multiplied by the ratio of any specific gas, the mole ratio of that specific gas, is going to equal the pressure of that specific gas. And we can say that for both gas A and gas B. And we will simplify that for all cases. And we're going to take the A and the B out of the equation. And just say for any gas, that's what I is standing for, any gas, the pressure of that gas equals the mole ratio of that gas times the total pressure in the container. And that just gives you the mole fraction. So this guy right here, this guy is just a condensed version of these guys. So instead of saying Na plus Nb, they're being more vague. They're just saying N total. Because they don't want to just say Na plus Nb. Because what if there's an NC, an ND, an NE? They want to be N total for completeness sake. Okay, so like I said, by the time you get to the end of the slide, you're going to need an example. At least I did. So here we go. Let's say we got a mixture of gases, a mixture of hydrocarbons. Okay, if you're making like propane, you'd probably run into this. You got a sample of natural gas, which contains a bulk of methane. Most of natural gas, or the gas that comes out of our spigots to light our Bunsen burners, is methane. You got 8.24 moles of methane. But it's not pure methane. You've also got 0.421 moles of C2H6, which is ethane, and 0.116 moles of C3H8, which is propane. If the total pressure of the gases is 1.37 atmospheres, what is the partial pressure of just the propane? The partial pressure just propane. Okay, so let's see how this is working now. Let's remember that final equation on the previous slide. The pressure of any gas is equal to the molar ratio of that gas times the total pressure of our mixture. Our total pressure is 1.37 atmospheres. We are concerned with propane. The end of this particular question says, what is the partial pressure of propane? It's a horrible color for a highlighter. I wish I knew how to switch it. Oh, I got it. I don't know how to switch it. How about purple? Oh, that's kind of cool. Let's do that one. Oh, yeah, see, it's like darker that way? That's still horrible. I don't know, I'll work on that. All right, so what is the partial pressure of propane? So that's why we're coming down here and we're using X prop. Okay, so X propane equals the molar ratio. So I'm just going to plug those numbers in. The top is the number of moles of propane, 0.116. The bottom is the addition of all of the moles of all gases inside of the mixture. Now, before I go on, let me ask you this question. Should our pressure due to propane be very close to the total pressure of the mixture? Or be only a very small fraction? Yeah, because it's not very abundant in our mixture. So we find that our mole fraction for this particular sample is 0.0132. Again, if you want to make that a little bit more visual, something that's a little easier to grasp, just think about this. Our sample is about 1.3% propane. That's more visual. I can see a pie chart or something in my head. So if we want to know the pressure just due to the propane, 0.0132 divided by 1.37, and there we go. So the previous slide, there's a lot of stuff there, and I think we use all these variables, and sometimes it gets confusing. But I would think, you can maybe agree with me that this particular problem is is not that tricky. This type of problem is relatively simple. The trickiness comes in when we don't just want to know about partial pressure, when we want to know other things, when we have to use this concept to solve a different problem. So water displacement to collect gases is such a common method, and actually you're going to be doing this Monday and Tuesday of next week in a lab, and we're going to do it in our activity today. It's such a common method that we've developed a table of pressures of water vapor at various temperatures. Okay? Remember what I said before? Water's always evaporating. It just evaporates more when it's warm. Well, if it's evaporating more when it's warm, there's more water molecules in the air or in the container, so they're contributing more to the pressure. Good? All right. So I've got a graph on the left-hand side here that just simply shows that relationship. So if it's very cold, okay, if it's very cold, the pressure in a container due to the water is really low. And as you get warmer and warmer and warmer, you start evaporating more and more water molecules. So you see the slope actually increase. Yeah, the slope does increase. Tangent, slope, increase, increase, increase. Okay, yeah. All right, good. So the graph is just a nice visual. The table here is the thing that you're actually going to use, and you don't have to copy this down. But what you should write down is there is a table of water vapor pressures on page 461 of your book. It's not as complete as this table. I like this table a lot more. And I should have put that table on that handout that I gave you, but I didn't. So if you need to reference water vapor pressures, which you should probably need to do over the next couple of days, page 461 of your book. If there's a temperature that's not in your book, then we can go online and find it. Okay? This table is from the new edition of Zoomdal's text, which is the one above us. So. All right. This is just kind of cool. I was thinking about scuba diving, and scuba diving has so many applications to this type of chemistry. So I just wanted to bring it to your attention. Have you all heard of something called the bends? Does anybody know what the bends are? That's correct, yes. Here's kind of an idea as to how the bends work. Let's say that you're scuba diving, and you're scuba diving responsibly, and you start diving. And when you do so, you dive and you descend slowly. So you go down a certain distance and you stop. Your body acclimates. Your tanks acclimate. Okay, everything is good. And you get down to 33 feet. You're now feeling twice the amount of pressure you would feel at sea level. But again, if you do this slowly, that's okay. Again, if you decrease in depth, you go down to 66 feet, you're now feeling 3 times the amount of pressure. Okay, it's probably getting a bit uncomfortable. But if you do it slowly, you're okay. But if you get down to that depth and, I don't know, you see it like a shark or something coming to chase you. Show my shark. Big teeth. I don't know, there's my shark. If you see a shark coming to chase you and you need to ascend at an incredibly quick rate, let's think about what happens. Pressure is going to decrease very fast. Okay? And Boyle's law tells us that if pressure decreases, volume increases. So the volume of the gases that is in your lungs is going to start to increase. Okay? That's going to be painful. The bends, okay, what happens with the bends is you're going to get, there's oxygen in your bloodstream. I mean, that's one of the main reasons we have blood, right? Oxygenate our body. So what happens is the oxygen in your bloodstream actually increases in size. Those oxygen molecules, the gas increases in size. And that's where you could potentially get the bend. And your body wants that pressure to escape. So I think one of the side effects of the bends, besides like dying, is blood rushing out your ears and your nose and trying to escape the pressure, trying to push it out. So.
I saw this 60 minutes on like diving in this remote area, like free diving, where people like sport where they go down like a rope. I don't know if it's like how deep it is, but it's like I want to say 1,500
They're down pretty deep. Yeah, they're holding their breath for like 8 minutes, 12 minutes, 20 minutes. I mean, it's ridiculous how long they're.
I saw 30.
What's that?
I saw 30. 30 to 30.
Oh, there's a 30 for 30 on it? Oh, I love that series. Yeah, that's crazy. Oh, and free diving, no scuba tanks. Just.
It's a sport, like to see how deep you can go, and then come back up, and then you gotta like say like certain things. And it's ridiculous.
Wow. I gotta check that out. That's cool. That's neat. Do they do any of the science behind it? When you saw the 30 on 30 or the 60 minutes?
I can't remember.
That'd be neat to see. Good place to show this. All right. Any questions? All right, that took 26 minutes, so Elizabeth is going to have to watch a 26-minute video.